Thank you very much. And the title of my talk is Application of Renormalization to Rotational Dynamics. Thank you. It's great to be here. And let me just start by saying what it is I do. So my field of research is complex dynamics. And what we do is we take a homomorphic function, we iterate it, and then we study the resulting orbit of complex numbers in one-dimensional case or complex vectors in higher dimensional case. And in complex dynamics, there's a basic dichotomy of points in the dynamical space that you're looking at. So the first type of sets is the Julia set. This is where the dynamics is chaotic. And then there's the complement of that, which is the Fatou set. And that's where the dynamics is stable. So here are some examples that I pulled from Google Images. To be honest, I don't really know what the colors mean. But I can tell you that the Julia set is on the boundary of these colors. So if you're near the boundary of the colors, then the orbit goes everywhere. And if you're inside the colors, strictly inside, the nearby points have orbits that stay close by. So as you can see, if you take a homomorphic function and you iterate it, and you get these very nice, rich, complex sets. And sort of one of the main missions of complex dynamics is to try and understand the topological structure of these sets and maybe say something about the analytic properties of these sets. Right? So for my research, I specialize to the kind of complex dynamical systems where a part of the dynamics is just rotation on a simply connected domain. And that domain is called a Siegel domain, or a Siegel disk. So to give you an explicit example, let's think about the most well-understood example, which is the quadratic polynomial with the Siegel disk. We call it a Siegel quadratic polynomial. So the standard family of quadratic polynomials to consider is what is called the quadratic family. And the formula is given by z squared plus c. Right, it's written there. And let's assume that c is such that it has a fixed point, and the multiplier at this fixed point, or the derivative of the function at this fixed point, is just some rotation by angle theta. And if you assume that theta is sufficiently irrational, whatever that means, I won't get into it. Yes. Well, I mean, if you have a continued fraction, then the terms, let's say, are bounded. Then it would be very irrational. Then we say that the fixed point is a Siegel fixed point, and it has the property that nearby that you can define a change of coordinates, so that not only is the derivative a rotation, but actually if you do this change of coordinates, the function becomes exactly rotation. Locally, but it's easy to prove that for the case of quadratic polynomials, it actually extends sort of globally to a whole disk, which is a Siegel disk. Right? So here's the illustration of the dynamics of this Siegel quadratic polynomial. You have the Siegel fixed point here, the domain, the component of this black region that contains the Siegel fixed point is a topological disk, and it just rotates by angle theta. The other black regions are just iterated pre-images of this Siegel disk. So under iteration, this black region will start sort of folding over itself, and eventually it will map to the Siegel disk, and then it will just stay fixed there. And outside the black region, well, since a quadratic polynomial is a polynomial, and for every polynomial, infinity is a super attracting fixed point. So if you go out to the white region, then the orbit of every point escapes to infinity. Okay, so that's sort of the basic description of the dynamics of the Siegel quadratic polynomial. And a lot of work has been done on this, on the dynamics of this polynomial. But I will just highlight two of them, which is relevant to my talk. The first one is sort of a local result. It tells us what's going on the boundary of this Siegel disk. So due to Duadi, Herman, and Chichikura, we know that if we assume that theta is sufficiently rational, then the boundary of this Siegel disk is a Jordan curve. Actually, we know more than that. We know that it's a quasi-circle, but we won't get into it. And also, the unique critical point of the quadratic polynomial, 0, is on the boundary of this Siegel disk. So that's the local result. And the global result is that the Julia set, the boundary between the black region and the white region, that is locally connected. What that means is the boundary, the Julia set, is actually parameterized continuously by a circle. And in this parameterization, the action of this polynomial, or the dynamics under this polynomial, is just the angle doubling map. So it's very simple. Right? And that sort of completes the dynamical description of this quadratic polynomial. We know everything that happens, right? So this thing rotates, everything else goes in. On the boundary, it's just angle doubling map, and everything outside just goes off to infinity. Right? So sort of my research has been to sort of look at what's been known, what's been proven for the Siegel quadratic polynomial, and try to generalize it to other circumstances, other contexts. So I look at three different situations. First, I don't look at a quadratic polynomial, but I look at a quadratic rational map. Second, I look at not a quadratic polynomial, but a cubic polynomial. And third, I look at sort of the analog of the quadratic polynomial in higher dimensions. So I look at a holomorphic function with two variables instead of just one complex variable. Okay? So let me just say what makes all of this research kind of tricky is precisely the fact that you have this critical point on the boundary of the Siegel disk. Because you see, critical point in complex dynamics is sort of the source of the nonlinearity and the complexity. So it's what makes the dynamics non-trivial. And what happens is that if you have this critical point and you iterate the map, well then near this critical point, the space sort of folds, right? Because there's a critical point there. And if it just folded a couple of times, just finitely many times, then it wouldn't be a problem. But what happens in this case with the Siegel disk is that, well, it's on the boundary of this thing, which moves like an irrational rotation, right? So this point just keeps coming back to itself infinitely often and arbitrarily close. So what happens is that you fold once, it goes around, and then it comes back to itself, and then it folds again, it folds again, it folds again. It folds infinitely many times. So near the boundary of this Siegel disk, the dynamics becomes infinitely nonlinear, and all the traditional methods, all these standard approaches sort of fail. Right? So we need something more advanced, something more powerful. And what I've used in my research is this technique called renormalization. Let me just give you sort of a general, vague description of it. I have to be vague because the specific details really depend on what kind of dynamical system you're looking at. But in general, renormalization is sort of defined like this. So let's say you have some dynamical system. It's a self-map of some space V, right? So you define renormalization by first considering some small subset of your dynamical space. Let's call it U. And then renormalization is defined by taking iterates on this smaller subspace until the points come back. So you take the first return map. And then the renormalization is defined as a rescaling of this first return map so that this smaller domain becomes the same scale as your original space. So it's a little bit, seems like a little bit meaningless. I mean, it's not clear why we do this. Well, the reason why we do this is because by renormalizing this map, you sort of factor the dynamics of F into two scales. So there's the macro scale, which determines the motion of this smaller subset through the bigger space V. Right? That's the macro scale dynamics. It controls the movement of this big set. And then there's the micro dynamics, which is the interior motion within the smaller subset as it sort of moves around in the bigger space. Right? So, and then when you rescale the smaller subset of the same size, of the same scale as the original space, what you do is you sort of zoom in on this part of the dynamics, right? And you ignore sort of the macro scale dynamics, and you just zoom in on the micro scale dynamics. That's sort of a vague, hand-wavy description of what renormalization does, right? And what I find fascinating is that if you do this on some class of maps, certain class of maps, then all the maps start to sort of uniformize to some universal function. So what that means is you take some class, you consider some maps in some class, right? And maps initially can look very different from each other. But if you start to zoom in on a certain part of their dynamics, then for some reason, for some mysterious reason, they all start to look alike, right? And that's sort of that's called a universality result. And the proper way to sort of phrase this theorem is to formulate the renormalization operator as an operator from some class of maps to itself. And then we say that you have universality, you have this sort of uniformization at smaller scales if this thing has some sort of attracting fixed point. Right? So you have this class of maps, you keep renormalizing, you keep scaling down, and then everything sort of converges to this one universal function. So how is this useful when we are trying to analyze the dynamics of a Siegel polynomial? Well, remember the problem was that you have this critical point on the boundary which keeps coming back to itself, right? And renormalization is the study of the first returns. So what happens if you apply renormalization to the Siegel dynamics is you can take some neighborhood around the critical point, iterate the map until it comes back, right? And then study the first return. And what several authors, including my own advisor, Michael Yampolsky, proved was that you have universality in this setting. So if you renormalize at the boundary of a Siegel disk, so you look at the sequence of first return maps, the smaller the domain you started with initially, the more iterates you take. So that sort of constitutes a higher degree renormalization. So if you look at the sequence of renormalizations, they converge to some universal dynamical system, let's say F star. So that's a universality result that was proved by many people in various settings and various situations, but I won't really go too much deep into it. I'll just sort of leave it vague like this. And sort of the key word here is the universality, right? So it's this thing, this fact that renormalization converges to some fixed point doesn't only hold true for a Siegel quadratic polynomial. It doesn't really matter in what context the Siegel disk is in. So for example, if we find the Siegel disk within the dynamics of some cubic polynomial, it would still converge to the same universal function. It might be inside a quadratic non-polynomial rational map. You do renormalization. It doesn't care that it's inside a rational map instead of a polynomial. It still converges to this fixed point. Or you could do it in some higher dimensional setting. You renormalize, it still converges to the same universal function.
What is the script F in this setting?
Script F? Oh, the script F, right. So that's sort of a very technical point. The one that I use is the space of commuting pairs. And the definition of that is kind of technical, so I won't go too much into it. Maybe in the question section I can go into it.
The Siegel disk is a commuting pair?
The Siegel disk isn't itself a commuting pair, but you can generate a commuting pair by taking two domains near the critical point, and then sort of iterating the map until it sort of goes into themselves. Yeah. So you can sort of think of it as if you take a rotation. Kind of wish I had a little bit of board space, so I'll just lift this slide. So if you have a rotation like this, right? You can consider it as a rotation, or you can consider it as an interval exchange map, right? So you could go from a rotation on a circle to a pair of sort of exchange maps like this. Yeah, so it's sort of a generalization of this, sort of a complexification of that picture. That's the space that we look at. Because as you sort of bring up, if you renormalize a map on a circle, it doesn't become a map in a circle. It becomes a map on an interval, on an arc. Right? So that's a technical issue that does come up, but you avoid it by considering commuting pairs. Anyways, okay, so this is sort of a vague description of renormalization. Now let me tell you, sort of give you a quick rundown of my results. Just for comparison, here is the visualization of the dynamics of quadratic polynomials. It's the very famous Mandelbrot set. Now this sort of is where all the quadratic polynomials live. So for example, z squared lives at the center of the main hyperbolic component. This is the Julia set. Here is the quadratic polynomial that has an attracting 3-periodic point. There's one here, it goes, I think, there, and then it goes there, and then it goes there, right? And then here is a Siegel quadratic polynomial. It's on the boundary of the main cardioid. This is the Siegel disk right here. So just put it here. This is a Siegel disk. Okay. And now let's try to generalize what we know for Siegel quadratic polynomials for some Siegel quadratic non-polynomial rational maps. I told you that every polynomial has a super attracting fixed point, so sort of a natural generalization you can make is to make this fixed point at infinity not a fixed point, but rather a periodic point, a periodic cycle, say a period 2, right? So if you consider the family of all quadratic rational maps with a super-attracting 2 periodic orbits, they form this basilica family, and the dynamics of that family is illustrated by this non-escape locus. As you can see, it looks very similar to the Mandelbrot set. And here are sort of maps in the basilica family that is analogous to the maps in the quadratic family that's shown in the slide. This is the unique member that has a super-attracting fixed point, just like Z squared is a unique member that has a super-attracting fixed point at the center. There it has a, there's a 3 periodic orbits right there. And then here is a Siegel disk.
What's the value of A for the first one?
Value of A for the first one is 1. Either 1 or minus 1. I think it's minus 1 or 1. I don't know. I forget. Yes. It's either 1 or minus 1. I'll just have to work it out. Okay, but you can kind of see that structurally the black region on the left side and the black region on the right side look very similar, because the conjecture is that you can get maps here, the dynamical systems here, by taking the quadratic polynomial with the super-attracting 2 periodic orbits, turning that white region inside out, and then gluing it to the maps you see on the left-hand side. And then you should get the maps on the right-hand side. So that's the conjecture. And it's been proven for almost every quadratic polynomial in the Mandelbrot set. The only exception are at the boundary of the hyperbolic components that are not too deep inside the Mandelbrot set. The technical word for it is it's only finitely renormalizable. It's actually less than 4 times renormalizable, and it's on the boundary of those hyperbolic components. Then we don't know if the corresponding map here is just the map here glued with that dynamics. So in particular, we don't know if this map is what we get if we glued this thing to that thing along the Julia set. And that's the first result that I proved, is that that is what it is, right? And really, the renormalization is key here, because the most difficult part of the dynamics to analyze is near the Siegel boundary. That's for the reason I sort of explained, right? But we know what happens at the Siegel boundary. There's a universality, and so on and so forth, right? So just from knowing what happens at the boundary, we can sort of use standard methods to sort of understand what goes on in the rest of the picture. Okay, so that's generalizing to non-polynomial quadratic rational maps. Oh, and there's nothing special about period 2, super-attracting fixed point and infinity. We can generalize to arbitrarily high periods.
What is the fixed part of the fixed disk?
So this disk isn't periodic. It just stays. So the generalization of a fixed Siegel disk, yeah, exactly, right? Yeah. All right, so that's the quadratic rational maps. Here's our work so far on cubic Siegel polynomials. So if you consider the family of all cubic polynomials with a fixed Siegel disk of a certain rotation number, then it forms this parameter space. All right? And this is work currently in progress with Mathieu Arfou and my advisor. And what we're trying to do is we're trying to come up with a topological characterization of all the maps on this in this parameter space, in this parameter slice, modulo what happens at the Mandelbrot set. So you have a small copy of the Mandelbrot set where sort of the bifurcations are exactly the same as in the quadratic Mandelbrot set. And not everything is known for the quadratic polynomials, so that sort of mystery transfers over to this setting. So we don't know what goes on there, but the problem there is just quadratic problem, right? It's not a cubic problem. So except for the mystery places with the Mandelbrot set, we should have the topological structure for all the other maps. But we're still writing it down, and we're not sure if everything.
That little Mandelbrot almost island has kind of factorization of the dynamical system, so it looks almost quadratic, or is it?
Yes. There's a way to cut out a quadratic polynomial if the cubic is here, right? Yeah. But for all other maps, we should be able to describe what happens dynamically. So that's sort of work in progress. And now let me describe in the last minute how to generalize to 2 dimensions, right? So in two-dimensional complex dynamics, sort of the family that plays an analogous role as quadratic polynomials are these quadratic Hénon maps. I just drew a little cartoon of what the dynamics look like. This is obviously just a scheme because it actually acts on C2, right? So it's a 4-dimensional space, and it maps to 4-dimensional spaces. But if we choose, you can see that the dependence on the second coordinate is controlled by the parameter b, right? And if you make b equal to 0, well, then the width of the image goes to 0, and the map just degenerates to just the plot of the quadratic polynomial f of c, right? So you can sort of consider when b is small, this is just a perturbation, small perturbation of the quadratic dynamics, right? So in this setting, we can get sort of a part of the dynamics to be rotation by assuming that there is a fixed point with multipliers in one direction of rotation and in the other direction contraction by nu. And we assume that the rotation is the golden mean, in which case we have that there is a local linearization, just like for one variable, near this fixed point, so that after a change of coordinate, the map is just a linear map, rotation in one direction and squeezing in the other direction. And just like in the one variable, you can extend this linearizing map globally to some 2-dimensional domain in C2 and the bi-infinite cylinder, D cross with C. And the dynamics here is rotation in one direction and squeezing in the other direction. So you can see that if you take any point in here, the orbit should converge to some disk at level D, at level 0, right? And this disk we call the 2-dimensional Siegel disk. Right? And to understand the dynamics of these Hénon maps that have these Siegel disks, it really comes down to 2 questions. One, we need to understand what's going on at the boundary of the Siegel disk. That tells us everything we would want to know about the local dynamics of these maps, and we also need to know what happens at the boundary of the cylinder, right, for the global dynamics. Okay, can I just take 30 more seconds? All right, sorry. Okay, so for the local dynamics, for what happens on the boundary of the Siegel disk, we've made a lot of progress. So first of all, we have the universality result for the renormalization. It's proved by my advisor and and a co-author, Denis Gaidyshev. And using that, they proved that just like in the one-dimensional case, because in small scales, the map, the 2-dimensional map, looks like a one-dimensional map. The boundary of the Siegel disk is also a Jordan curve. And my advisor and I proved that just like in the one-dimensional case, this thing cannot be smooth, right? And then I was able to improve the universality result. So not only do we know there is no critical point, no. Exactly, right? Yeah. Yes, that's why it's not just a trivial thing. Yeah, that's right. Exactly. And then, right, so I was able to improve on the universality result. So not only does it sort of converge, degenerate to a one-dimensional map, we also know its behavior, sort of 2-dimensional behavior as it converges to the one-dimensional map. And using this, I was able to prove the first sort of truly 2-dimensional result about the 2-dimensional Siegel disk, that it's not rigid at the boundary of the 2-dimensional Siegel disk. So there's no C1 conjugacy between different Hénon maps with the Siegel disk of the same rotation number. Right, and the remaining question is, so now we know what happens at the boundary of the Siegel disk. In the one-dimensional case, we could sort of use that to sort of understand what happens everywhere else. Sort of, can we try to do the same thing in this case with the 2-dimensional case? And that's sort of the main thing that I'm interested in. All right, thank you. I went over time. That's it.
Can you go back
Yeah.
to the non-rigidity result? What's the precise statement?
Oh, so the precise statement, I mean, it's
This is C1 on there.
On their Siegel boundary. So if you consider 2 Hénon maps with a fixed point, the rotational eigenvalue is the same, but you make the amount of squeeze different. And then on their respective Siegel boundary, they're not C1 conjugate. They're not smoothly conjugate. So there you have a conjugacy between the Hénon map and just a rigid rotation on a circle on the boundary of the Siegel disk. So if you sort of compose that, it's not C1. Yeah. And this is different than...
To the rotation example.
Well, it's not C1 conjugate to each other.
Oh, the two.
Yeah, but for these two. Yeah.
So what does it mean? This is a kind of a fractal or fractal
Yeah.
set.
Mm-hmm.
So what do you mean by C1?
That's a good question. So it could be that the Siegel boundary for one map is just a smooth image of the Siegel boundary of the other map, right? And this smooth mapping also conjugates their dynamics.
Smooth in the four-dimensional space.
Yeah. Smooth in just not in a complex sense, just in a real sense. Just C1, yeah. But it can't be. And this is different than in the one dimension where, in fact, if you ask the analogous question.
Are the Lipschitz equivalent?
Oh, that I haven't thought about. Lipschitz equivalent, I think no. Right? Yes, that's right. Yeah, there's a bound. There's a bound on the Lipschitz exponent. And the Holder exponent, yeah.
Bound on that,
Yeah.
But the Lipschitz is much stronger statement.
Right, so I haven't quite thought about that, no.
Oh, they're not? Oh, so they're not the Lipschitz.
Yeah, there you go.
Oh, they're not Lipschitz.
Okay, thank you.